Hello, this is episode 6C. We're going to be talking about classifying the critical points of quadratic forms. So, really briefly, we're just going to talk about quadratic forms, what those are if you have not touched on those before. So, we're going to take a quadratic form, looks like this: ax squared plus 2bxy plus cy squared. They don't, so if you don't know what a quadratic form is, you probably want to review that, but I'm not going to look into that right now. But this is just a particular type of quadratic form, right? And so a, b, and c, these are constants, right? And then so what we can do with these quadratic forms, we can actually turn this into a matrix, right? But right now, what I'm going to worry about is let's just worry on taking the gradient of this function. So we take the gradient of f. Well, then this is going to be, the 2's come around. So this is ax plus b y, right? And then this comes out as, okay, bx plus cy. This is our gradient. Now, what can we do with this? Well, this looks awfully like a matrix multiplication, right? This is actually just, the matrix A, B, B, C, X, Y, right? X, Y. And so, well, what do we see? If this matrix is invertible, then it has, so I'm just going to label this matrix. Yeah, we'll deal with this later. So if this matrix is invertible, right, its determinant is non-zero. That's what that's saying. Its determinant is non-zero if it's invertible, right? And so what is its determinant, right? So its determinant is ac minus b squared. Does it look a little familiar? Right? A times c minus b squared, right, is not equal to 0. Right? And if that looks familiar, remember that we had x fyy minus f of xy squared is not equal to 0 for our critical points. So this is going to come, this relationship will come to play later. Just keep that in mind. Keep that relationship in mind. But for now, if we do actually happen to take f of x, so we have our gradient, but let's just look at what f of x is. So, or let's just take the second partial derivatives. Okay, let's look at this. So, f of xx, well, that's a. F of yy, well, that's c. F of xy, well, wait a second, that's just b. So really, for quadratic forms, these are the same thing. This is the same formula, right? We're really taking the determinant of this, this matrix, right? So for quadratic forms, we can have this form here. If a is greater than 0, you can basically say the same things. If a is greater than 0, and d is greater than 0, then a is a minimum, right? If a is less than 0 and d is greater than 0, then some critical point a is maximum in our quadratic form. And then 3, if d is less than 0, then there is a saddle point. And so because this is a quadratic form and we just have this a is going to be 0, So this is a saddle point, right? Because that's just the roots of these, right? What critical point? What's the critical point? Well, that's just asking when is this 0, right? Well, if this determinant is non-zero, then the only thing that can be 0 is these guys. And since these A cannot be 0 and B cannot be 0, right? So yeah, so we have to basically just match this x and this y, and then so the only critical points are for these quadratic forms is the 0 vector, right? And so that's kind of what we're looking at here. This is with the 0 vector. So and so this kind of becomes important. This kind of becomes kind of crucial, right? And if you know from linear algebra, we can rewrite quadratic forms, right? We can actually rewrite this as 1 over 2 xy a b c d x y. Interesting, isn't it? And so we're gonna do some other matrix magic. This is kind of where calculus starts to meet linear algebra. So we're gonna start using some other linear algebra stuff. So recall that if a matrix is symmetric, it is equal to its own transpose or its own Hermitian transpose, I guess. But we're only dealing with real numbers for now, right? We have a symmetric matrix, which has this property. Then its eigenvalues are real numbers. And its eigenvalues are orthogonal, right? So if you remember that, what that means is we can actually decompose. So I'm just going to say this matrix is D. We can decompose D into some matrix. Actually, probably D is not the right way to put it, but we can decompose into some U, transpose, and then P, U, right? And in this case, since we can diagonalize it like this because these U, these are inverses of each other, right? So if you're not familiar with this, you might want to review some linear algebra. But we can use this property, and then we can substitute this for D. So we actually can use f of x y is equal to 1 over 2 x y x y u, whatever u is, transpose, and then our eigenvalues, right? X, y. And if you know the matrix property, this matrix multiplication, its transpose is x transpose a transpose, right? These are the same. So we can actually use this, and we can write this as 1 over 2 u, and I'm just going to use a shorthand, x transpose p ux, right? And I'm going to suppose, so I'm going to do some shorthand. Suppose u, whatever u is, times xy is equal to v1, v2, okay? So it's equal to, this is going to be equal to v. Then well, we can substitute this in here. Again, do one more substitution. So we got v transpose p times v, right? And p, this is p. It's just this diagonal matrix of its eigenvalues, right? And then this is just equal to 1 over 2 times lambda 1 v1 squared plus lambda 2 v2 squared. And so what can we get from this? Well, if lambda 1 or lambda 2 are greater than 0, then this expression, I'm just going to call this expression E for simplicity, right? This expression E is greater than 0, right? So if both of these are 0 or greater than 0, right, we add two numbers greater than 0, then this expression is going to be greater than or equal to 0, right? So we have a local minimum, right? We have a local min, right? At the, I guess it would be the 0 vector, right? Because that's the critical point. And if we have the opposite case, so this is actually less than 0, well then the opposite is true, right? A negative number plus a negative number is going to be a negative number, so this is going to be less than or equal to 0. So that's actually a local maximum, right, at 0 there. So how do these connect to D exactly? Well, the connection between D and the eigenvalues is that the product of the two eigenvalues is equal to D, and D is not to be confused with this matrix, but D is equal to, you know, our f of x, f of y, minus f of x, y squared. So we have these eigenvalues. And if so, they both have the same sign, right? Then if they both have the same sign, then the product is going to be positive, right? So if they both have the same sign, they're both positive or they're both negative, then D is going to be greater than 0, right? If their product is greater than 0, right? If one is negative, so if one is negative and then the other one is positive, then their product is going to be less than 0. D is less than 0. So we have a saddle point. So we have a saddle point for quadratic points, we have a saddle point if one of the eigenvalues is not, if one of the eigenvalues has a different sign than the other eigenvalues. And this obviously works for all the other and actually, if you're curious about where this relationship comes from, this D, remember that D is equal to this, and all we have to do is we just take, so we just want to find, okay, this determinant is equal to the determinant of this, right? And then the determinant of P is going to be, the determinant of P is just the diagonal. Okay, but yeah, so when if one of the eigenvalues of our quadratic form, it happens to have a different sign to the others, if one or more of them have different signs, then we have a saddle point. That's what that's saying. So I'm running out of space, but yeah, that was a lot, but hopefully that makes sense. And we're gonna move on to some theorems of how actually we can use these to actually classify quadratic forms, or the critical points of quadratic forms and other functions, because we can actually use quadratic forms to approximate other functions as well. We'll get into that. So see you then.